In this video, we're going to begin investigating some of the commonly seen reactions in organic chemistry. The first one that we'll discuss is an oxidation-reduction reaction. In an oxidation-reduction reaction, commonly known as redox, electrons are transferred from one reactant to another. The reactant which loses electrons is said to undergo oxidation, or is oxidized. The reactant that gains electrons is said to be reduced, or to undergo reduction. There are a couple of nice acronyms to help you remember this. One is oil rig, in which oxidation is loss and reduction is gain. My personal favorite, though, for remembering these, is Leo the lion goes grrr. Lose electrons oxidize, gain electrons reduce. I know it seems kind of silly to think about it like that, but I guarantee if you memorize Leo goes grrr, you will always remember what is being oxidized and what is being reduced. This process is pretty easy to see if we actually investigate what happens to the oxidation numbers, or the charges, in the case of certain reactions. We have to remember that anything in its natural state, such as something like magnesium in its solid form, or hydrogen in its gaseous form as H2, will have a charge of 0. And so in this reaction, in which magnesium is reacting with hydrochloric acid to form H2 and magnesium chloride, we can see that magnesium is going from a charge of 0 to a charge of 2+. Whereas hydrogen goes from a charge of +1 in HCl to a charge of 0 in H2. And so we can separate those out. We can see that magnesium, going from a charge of 0 to a charge of 2+, is losing electrons and becoming more positive. Thus, it is being oxidized. Whereas hydrogen is going from 1+ to a charge of 0. Therefore, it is becoming more negative and gaining electrons, and so it is being reduced. We can look for a couple of different things when trying to determine if a redox reaction took place, or to try to determine what has been oxidized or what has been reduced. In an oxidation, as in the examples we just looked at, we can look for a loss of electrons. However, we can also see if a reactant has decreased in hydrogen atoms or increased in oxygen atoms. The opposite is true in the case of reduction. If something is being reduced, it is gaining electrons. However, we might also see, depending on the reactants, an increase in hydrogen atoms or a decrease in oxygen atoms. And we'll take a look at some examples of that. Here we see several different types of carbonyl compounds. We can see that if we have a primary alcohol which undergoes oxidation, we're going to form an aldehyde. And we can see that our carbon atom has decreased its number of hydrogens, going from the alcohol to the aldehyde, and so that is one way to know that it has been oxidized. Aldehydes can then be oxidized further to a carboxylic acid. And now the carbon is increasing oxygen, and so therefore it is being oxidized. It's not written in this chart, but the reverse is also true. And so if we have a carboxylic acid and reduce it, we can form an aldehyde. The aldehyde can be further reduced to form a primary alcohol. A secondary alcohol could be reoxidized in order to form a ketone. And the reverse would be true. If we have a ketone, it can be reduced in order to form our secondary alcohol. Primary alcohols cannot be oxidized to form anything else. Another type of reduction is known as catalytic hydrogenation. In catalytic hydrogenation, an alkene, a C double bond C, can be reduced to form an alkane and remove our double bond. We can see that in doing so, hydrogen is added to each of the carbon atoms. Next we come to hydration and dehydration reactions. In a hydration reaction, water can react with an alkene in order to produce an alcohol. The H and the OH atoms from the water molecule form bonds on either side of the double bond. So in this example here, we see propene, and we can see that the water molecule, our H and our OH, are going to then join the carbon atoms on either side of the double bond. And so we can see that our OH is attached to our central carbon. So the OH attaches to this carbon right here, and then the H attaches to the other carbon, and our double bond disappears and forms a single bond. In these types of reactions, the OH is always going to form on the carbon that is more substituted. By that, we mean that this carbon is connected to two other carbons, whereas this carbon was only connected to one. And so the OH forms on the carbon that is connected to other carbons, which means we form propan 2-ol rather than propan 1-ol. The opposite will occur in a dehydration reaction. In a dehydration reaction, we have an alcohol, in this case our propan 2-ol, and a dehydration reaction occurs to remove H from one carbon and OH from the other. So we form water as a product, but in that removal, a double bond will now form between the two carbons so that carbons are able to retain their octets. In a dehydration reaction, if more than one product is possible, the more substituted double bond will form. In other words, with this alcohol here, we could potentially form our double bond on this carbon-carbon bond, or on this carbon-carbon bond. And so what we actually see is the formation of the double bond between carbons 2 and 3 rather than between 1 and 2, as that is more substituted. And this is known as Zaitsev's rule. So in this video, we have explored oxidation-reduction or redox reactions, as well as hydration and dehydration reactions. In the next organic reactions video, we're going to explore group transfer reactions and hydrolysis reactions.